Hello, everyone. Welcome to our second lecture on the processes associated with climatology, specifically focusing on atmospheric, hydrologic, and then the ocean processes. So this lecture is really all about the ocean currents and the processes that couple, as you've sort of figured out now, with the atmospheric and hydrologic processes. So fun fact for the day, let's talk about this polar vortex thing. So I've alluded to it a couple of times. It's certainly all over the news right now, especially last couple of weeks, as the East Coast has been pretty well pounded, right, by some cold weather. So you know that the polar vortex is not a new thing now, right? You've read that, you've seen those in the circulation models, right, right here, polar high, polar easterlies. That's the vortex that they're talking about, right? And it typically just stays up there. However, this can be broken down by a number of things, primarily the jet stream. When the jet stream gets a little out of balance, it tends to swoop down right here. And we know the jet stream gets out of balance for a couple of different reasons. One is, the warming in the upper parts of the atmosphere. So these extreme warming events that occur. And if you remember from a few weeks ago, we had a fun fact of the day. The stratosphere was something like 90 degrees Fahrenheit above average over Alaska. So it's absolutely no surprise that we had this breakdown of the jet stream. We're not a breakdown, but it's got this wobble now. Instead of being just around the pole, it's got this wobble that swoops down, and this is a pattern that's been repeated over and over again. And there's been some, there's a much a longer history than just the past decade or two. There's some real strong examples. Go back to the 80s and even the 70s of this polar vortex dipping down into the East Coast and having this. So remember, as you're watching the news, this is not a new thing, um, but I'll also leave it up to you and your interpretation as we talk about ocean circulation to see if there's something with this polar vortex that might be related to that. All right, so remember we're talking about atmospheric circulation. In last lecture, and we were talking about all the Hadley cells and the subtropical highs, or the horse latitudes, whatever you want to call them. Basically those dry spots that correspond really well with deserts because that's when it runs out of moisture in the atmosphere as the air comes down. It sucks it all up from the land, creating really dry land surface or dry land um, areas. And then it eventually warms back up and goes back up into the cycle due to all that solar radiation at the equator, right? But then since we're moving, we've got these wonky centrifugal force, the Coriolis effect, kind of playing at the distribution of that solar radiation through the atmosphere, through these trade winds and easterlies and westerlies. And all the while, so we're kind of working in three dimensions, right? You got east west, and then you got in the y or the z direction, you're going up into the atmosphere. And this has big implications, obviously, on where we see precipitation and temperature extremes like the deserts, and where vegetation is really good because it's a consistent source of rain. We also talked about the heat capacity and in the sort of the relationship between the hydrologic and the atmospheric circulations, and just that water can hold so much more energy. And we know this intuitively, and we know this scientifically. We have all kinds of empirical measurements to suggest this. Obviously, the ocean plays a significant role in this, and absorbs about 90% of the Earth's energy, our sun's energy coming into the Earth. And there is some uncertainty with all this, but certainly ocean has and the water capabilities or water holding capabilities are much more significant than the terrestrial piece. So what does that mean then for ocean circulation? Because we know the water doesn't stay put. I mean, we know that we at least have the tides, right? But actually we have these much larger movements of water. And you also know now too, right? We've got different depths of water that maybe move at different time scales or in different directions. And so we've got these basic five large gyres throughout the world, right? That are all defined specifically by their unique geography. We've got the Gulf Stream that exists primarily because these easterlies hit the surface and then it swoops it around. Same kind of thing here. You get this real strong westerly hitting the land masses. You get this spinning effect then as it kind of circulates around the North Pacific. Same with the Humboldt circulation or the gyres. It's very well defined. And then you get the Indian Ocean one out here too. It's it's very well defined because of the specific location of planets and tectonics, the ocean surface or the ocean ground, and all those things. So how does this relate then to temperature? Well, the red arrows indicate the movement of warm water, right? So those are coming off of the equator and the mid latitudes, because that's where most of the solar radiation is hitting, right? And it's moved upward through that upwelling process or that downdwelling process. It's moved across here. Well, it's hitting land masses. It's swooping up, and then through the downwelling, right? It cools down as it slowly cools off up here. It sinks back down. That creates a pressure differential, which then pushes that warm water back up again. And this is the repeating feedback loop, right? It's a feedback loop in that you're always getting constant inputs and outputs that are the result of this. So we see these red arrows, and they're distributing energy in places that maybe the sun can't quite get to, and that's really crucial, right? So it's not only just sort of at the surface, but it's also the deeper water currents that are kind of playing a role in this redistribution of energy across the globe. So it's very clear from these, right, that you can see most of the warmth is coming from the equator, and as it moves up, it cools down, but it is redistributing all this warmth to the upper latitudes. This one being the most famous one, right? This all plays in with the fact that the ocean is super stratified. So that temperature differential has a role, but so does the amount of salinity. So ocean is highly stratified, unlike the atmosphere. The atmosphere is stratified, but it's pretty well mixed. It's not nearly as neatly stratified and stably stratified as the ocean, and it's simply just physics, right? Dense water hangs out below lighter weight water, less dense water, and density is driven primarily by temperature and salinity. And so you've got the upper surface or the upper parts of the ocean, about 200 meters, maybe up to 400 meters. That's primarily absorbed. That's the source of that solar radiation. So that's the stuff that's warming up and cooling down the most. But it's really in that's what you see largely in those gyres. You see that warm water moving around and turning into cool water. But when it turns into cool water, it actually changes density, right? Because cooler water tends to have more salt concentration or higher salinity levels. And if you remember that from the book, it's because if you extremely cool down, right, you actually start to form ice, and ice only forms with pure water. So you're actually taking that water out of the ocean as the salinity dissolving kind of phase of water. So you leave out that extra salt. So as water freezes, it actually, it's just the water that's freezing. It's not the salt in the water that's freezing. So that actually increases the salinity, which drives this density downward, or drives that water downward because it becomes heavier, it becomes more dense. And this all happens in this magical spot called the thermocline, right? So you can kind of see that temperature. I mean, it's just a dramatic drop off in temperature from the surface down to about 200, all the way up to maybe 400 meters, where you have that solar radiation influence. Beyond that, it's really primarily driven by salinity, and then to some extent the turbulence caused by like topography and on the Earth's or the ocean floor, because turbulence is super weak, kind of generally through here and, until you get down all the way down to the bottom. Um, so I like to think of these circulations definitely in animations, and this is a really nice one put together by NASA um, that doesn't have any sound, but it kind of shows these gyres and the Great Ocean Conveyor Belt really playing out. So you have the gyres at the surface water or the surface of the ocean, right, primarily, and then what this Great Ocean Conveyor Belt shows is when that gyre kind of goes and changes that temperature, right? So the warmer water's up top, it gets cooler as it's closer to the poles, it drops down, and it moves into these deep water, deep conveyor belt or deep circulation kind of routes. And you've seen this, right? You've seen this in the exercise to some extent. Um, but this is just such a nice visualization. And remember, this is all driven by pressure differentials in the salinity, which therefore impacts the temperature, and so you get this feedback loop causing this separation between the warm and the cold water pathways there, right? So it's really cool. You can kind of see it play out. Obviously, water that is not stuck in a place at any moment, right? It's not stuck in one guy or another. It's not stuck in one ocean or another. It's kind of constantly moving around. It's pretty impressive, and that creates this redistribution of Earth's energy, right? And it's just really important to remember that these cold and warm water and surface and deep water don't really mix except in those specific cases, right? Except in those special areas like up here in the North Atlantic. This is a really key zone because that's that transition from cooler or from warmer, sorry, into cooler, and it sends it on a completely different pathway. Otherwise, those physics really just keep those two systems separate, the warmer water and the colder water, the shallow versus the deeper water, because of that strong, stable stratification that I was talking about. So it's not until you get into those certain areas that it works out, where you get that mixing. And it is largely driven by the location of the poles and just that the freezing water and intensification of salt. All right. So what does this have to do then with kind of our number one metric in this class, right? Temperature. How does the circulations and this redistribution of heat, how does that play out in our ocean temperatures? Because obviously we're going to see a manifestation, right? If it's funneling energy along the top of the ocean initially, and then getting deeper and going into these deep cold water reserves and then coming back up and get warmed up. We're going to see some of those patterns, and yeah, you definitely do. So this is another animation by NOAA, but this one shows sea surface temperature from the mid 80s to 2007. And gosh, is it really cool to kind of watch that first, the undulation from the seasons, right? You get the northern hemisphere warming up, and then you get the southern hemisphere warming up annually. Pretty neat stuff. But kind of start watching the North Pacific. There's the El Nino La Nina kind of dichotomy, right? And you don't, it's not one or the other necessarily, but we think of those two as the opposite kind of effects. And specifically look for it here coming up about 1996, 97, 98. So 97, 98 was this really strong El Nino year. And what you'll see is just this incredible warming down here that isn't normally there, right? Well, not normally, but not annually there. It is a normal process, but it's not annually there. And this had big implications, right? I'm going to talk about that here in a second. But so you kind of see just how that warmth gets distributed up via the Gulf Stream, back down, up, back up the Gulf Stream, and you see this playing out, right? Like you see this circulation happening. This is what warmed up Europe, keeps it from freezing because otherwise it's the latitude of like most of Canada, and Canada is a little colder than Europe typically, right? But you see these mixing zones. You see how that great conveyor belt kind of just distributes all that heat evenly across the ocean. Well, mostly evenly across the ocean, except not as much up here, right? Like it's fascinating. And this is why Alaska's, sort of one of those quintessential great places to catch, lots of fish because it stays cold persistently. There is no circulation to really, really warming that thing up. So let's talk about El Nino, La Nina real quickly because it's not in the book. And I feel like that's just one of those main take homes that we all want to know about, right? So just a quick reminder, because I'm sure you've heard it in other classes. El Nino is just it causes that it's a warmer than usual, average, whatever you want to kind of use. Warmer chunk of air where you get this extended Pacific jet stream gets a little amplified. I think there's even like archaeological evidence that the ancient Peruvians, like used to do sacrifices to avoid the El Nino because it would basically just like hammer them with rain. It was kind of fascinating to read sort of the longer history of El Ninos. But it moves really far south. So the jet stream just typically isn't that far south. So what this does is it creates just a ton of precipitation for the southeast, in particular, and it really warms up and dries out sort of the Pacific Northwest and the Rockies. I mean, growing up in Denver, El Nino years were the curse, right? That was when Vail and Breckenridge and all the ski resorts would just be on the brink of bankruptcy, and I remember always that playing out. And that 97, 98 winter was one of those for sure. But look here too, like look at sort of how low the polar jet stream is sitting, and isn't that interesting? And this is different than the La Nina year. And La Nina years, where you basically get those stronger easterlies pushing all that energy back. So La Nina, these easterlies basically they sometimes just don't even exist, which means all the warm water kind of sits off here. It's actually a little bit lower here, but that creates this lower jet stream. Well, the La Nina is the opposite, right? You get really strong easterlies pushing all that warm water this way, so you get a cold pocket of water here. The ocean is colder generally during the La Nina, and that sets up a jet stream up here that's still super variable, but generally results in wetter here, drier down here. This is kind of what we're seeing this year, right? At least the other parts of the Pacific Northwest are just getting hammered with precipitation. But look too how far this colder weather kind of droops down. And so, I mean, thinking about this polar vortex, it's kind of important to think about the context of sort of the El Nino, La Nina kind of relationships. It's not as strong on the east, obviously. This is a ENSO, the North Pacific kind of oscillation. This is a Pacific Ocean kind of driven thing. So of course we're going to get most of it in the West Coast, but it's really important to kind of just think about the context of this. But yeah, I figured we needed to talk about this because so often we see these El Nino, La Nina years, and it confuses people on why. It confuses people on our ability to detect, these longer term changes in, say, ocean temperature. But in truth, like we know these patterns very well. They're very easy to, even predict, right? Like we have a pretty good probability predictions. But certainly once we're in it, we have a very good way of documenting it and understanding what happens. We're not totally there, like on the long-term forecasts of like, are these El Ninos and La Nina cycles going to get stronger, as we continue to warm the ocean or whatnot? But it's still very easy to identify. And this is key because right? The book kind of talked about like we have warming across the ocean. We would expect that, right? If the ocean absorbs 90% of the incoming solar radiation, um, then we would expect that that the ocean would start to warm, because we know that the amount of radiation emitted, terrestrial radiation, the stuff that's hanging around in the atmosphere, is increasing. So that's absorbable energy from the ocean, and like I said, 90% is absorbed in the ocean. So we see that reflection in the temperatures. So the book kind of had this nice four kind of diagram map series showing the surface temperature of the ocean, top 700 meters. And you've seen this before, remember, back in chapter 2 or 3. So we know that the ocean has warmed significantly in some places. It's got little pockets cooler, but generally has warmed. It's not completely even across the globe, right? With that, we've actually seen a significant increased, sort of trend, right at 60 degrees north. It happens to be kind of right here. Well, right where Anchorage, I think, is 61 degrees, if I remember correctly. So right, sort of, it's pretty far up there. So we see this significant warming. It's really pronounced in the North Atlantic, and then we see it, and this is the most significant point, across all the depths of the ocean. So if it was, the hypothesis, out there that, the ocean circulation has caused the observed warming that we see, if that was the case, that would only be true if we saw stronger stratification, stronger temporal or thermal stratification, right? Because the circulations would be amplified only by an intense cooling down here and an intense warming up here over time. But we don't see the cooling. We see warming, all the way across, or all the way down in the depths, and that signals then that it's simply absorbing more energy, more temperature from the Earth's atmosphere. And that increased temperature is there because of that emitted thermal radiation, right? And the fact that it's not escaping back out into space. And this just shows the temperature difference between 200 meters and the surface. And again, just kind of really highlighting that, yes, indeed, everything has been warming in the ocean. So this then has some pretty big implications then on salinity, right? And so acceleration of the hydrologic cycle, as we were talking about before, affects the salinity of the oceans. And the salinity drives this temperature relationship, right? But regions that are already salty, such as the subtropics and Atlantic, get even saltier. And areas that are already fresh, like the North Pacific and the Southern Ocean, get even fresher, because with that increased evaporation, right, comes increased potential precipitation. Evaporation happens, so that vaporization of water happens a lot easier when it's less salty, right? So the areas where it's less salty are going to increase that potential evaporation, therefore leading to even more rain. More rain falling on it increases the freshwater. More rain falling on the terrestrial part increases the freshwater fluxes, right? And same for the places where it's salty. So it's kind of this, it's part of that feedback loop that gets us further and further more into the extremes. And so this just shows the mean sea surface salinities, and this is the sea surface salinity change. Can't remember what the time frame is on that, but so that kind of covers the ocean side. So remember, all three of these things are kind of intricately connected, and this is why the book, in other climatological books, they actually separate the atmosphere and then have a whole chapter on the hydrosphere, and then a whole nother chapter on ocean circulations. And I kind of like that he kind of treated them all together as one, because really it's very hard to disentangle, right? I mean, it's kind of like ecology. it's really hard to separate out one, food web from another, one species from another, or one functional relationship of herbivore to plant than another, because they're all working in tandem. So the atmosphere, the hydrosphere, the ocean, they're all working together. They're balancing each other out. They're feeding into each other, and they have these stasis states where where energy is kind of evenly distributed. And yes, there's natural fluctuations to that, but what we're seeing is that we're starting to exceed those natural fluctuations across the board, both in terms of the energy distribution and in terms of local manifestations of that. So that's it for processes. Next week we get to start moving into how do we model all this.